Hello, everybody. Today we're beginning our discussion about momentum. So I'll add my 2 cents to what the textbook might be talking about. Momentum is one of the fundamental principles that we have. So we're going to introduce it as a conservation principle, where P is momentum, and momentum is a vector. And that's going to equal to the impulse. Which will also come at us as a vector. Momentum itself, we have to take from Einstein. And he defined the momentum quantity as mass times velocity over this correction factor we saw when we did energy. And as we saw when we did energy, this only comes into play if we have very large velocities. So velocities approaching the speed of light. Fortunately, we don't usually deal in that realm. We usually deal with small velocities. So a small velocity divided by a huge velocity gives us a very, very small velocity. Then we're going to square it so that teeny tiny velocity becomes smaller and smaller and smaller as we square it or cube it or quarter it or everything. So we usually take momentum as approximately equal to mass times velocity. Notice, however, that momentum is going to be a vector. Prior to Einstein, and part of the reason why Einstein being able to derive this formulation was so important, was we had traditionally used F equals ma. So that we have all of the forces that are acting on the mass system, and they cause an acceleration. This assumes the mass is constant. What if the mass is time dependent? So I'm going to write the mass of the system. We'll expand the acceleration out to its definition. So I'm going to have dv over dt for the acceleration. And then we're going to make the assumption that the mass of the system does not have to be constant. And we wind up with the derivative with respect to time of the mass of the system and the velocity of the system. All that is going to be equal to the sum of the forces. So we then do the integration on both sides. So I'm going to get the integration of all the forces that are external to the system multiplied by dt, the time interval, is going to equal our momentum quantity. And this then is all based on the system. So no matter how you talk about it, we know that momentum is defined as mass times velocity. And it's a vector quantity. What now becomes interesting from a philosophical viewpoint is that when we did F equals ma, and the mass was just a point particle, we made the assumption that we could apply it to anything. You know, cars, trolls, you name it. So, but all we were really doing was thinking about them as point particles. We drew our free body diagrams as point particles. And with the introduction of the idea that the mass can change, we're allowed to build objects made of point particles. And that's all due to Newton's third law. Newton's third law says that if I have two objects, that this guy will be attracted to the first one. So let's label them 1 and 2. So the force on 2 from 1 should be equal and opposite and acting along the same line as the force of 1 on 2. And these are vector forces. So if they are inside of my system, I'm going to have to add them together. So if I define my system as including both of these tiny little masses, then the interior forces will add to 0 when I sum up all the forces inside the system. So sum of the forces in the system, they're all going to add to 0. Suddenly we can start doing collisions with real objects and not have to worry about the fact that they're just point objects. We're still going to be constrained by something that's called rigid body at this point. And that's just an assumption to make our lives easier, our rigid bodies. But that just says that the mass doesn't change shape much. So that I can always make the approximation that the forces internal are going to be equal to 0. So this is the idea where this principle comes from. From the external forces, we get impulse. Just like the external forces gave us work, but remember, work was force external times distance. Now with impulse, I get force external multiplied by time. And that gives me then on the other side a change in our momentum for the system we define. So that's the basics of where the conservation of momentum comes from.